Hello, everyone. Welcome to our talk, which is entitled Smart IoT, IoT botnet attacks on power grids exploiting their weak points. So let's start with the Smart IoT team. I'm Tauhid Shikari, a PhD candidate at ECE Georgia Tech, and this is a joint work with my PhD advisor, Dr. Rahim Bea, who is leading the Communication Assurance and Performance Group in Georgia Tech. Now, before explaining the attack and the issue, I would like to start with a brief background on the power grid structure. Generally, every power grid has three main sectors, which are called the generation sector, transmission sector, and distribution sector. In the generation sector, we generate a major portion of the energy required by the customers and the end users by big power plants such as nuclear power plants or wind farms or the solar farms. And then we transmit the power and energy over long distances using the transmission lines. And finally, in the distribution section, we distribute the energy among the end users. Like any other industrial control system and big system, power grid has its own monitoring and control network, which is called the supervisory control and data acquisition system. So basically, in this computer network or monitoring and control network for the power grid, we have multiple substations in which we have the monitoring devices and also the control devices. So the monitoring devices, such as the measurements, such as voltage sensors and current sensors, are polling the measurements in these substations, and they are returning back the readings to the control center, and the control center processes those information, and they have some automated tools or human operators to decide about the control actions to be implemented in the substations. The control actions could be switching some circuit switches, or even changing the configuration of the system, or increasing or decreasing the power generated by different power plants to meet the new requirements of the grid. So with the explosion of the computation and communication technologies in recent years, the concept of smart grid has been introduced. Smart grid is the old grid in which we have the integration of the recent advances in the computation and communication. This obviously led to a better management of the system, cheaper energy, but at the same time, because we digitalized everything and we made everything smart, we increased the attack vector to cyber criminals around the world. Now let's talk about the IoT botnets. So IoT botnets were seriously introduced by the discovery of the Mirai botnet in August 2016. And it included more than 600,000 compromised devices. And this botnet was mainly used to indirectly attack the other domains, such as the Brian Krebs website. And in this website, the Mirai botnet was used to do the distributed denial of service, just to make it out of the reach of the users in the web. And after this Mirai botnet, there were some modern variants of it that were introduced in recent years, such as LuaBot, Hejime, and BreakerBot. Now let's talk about the power grid attacks. So generally for the power grid, we have three main types of attacks. In the first type of the attack, the attacker might target the local controllers of the standalone devices. The local controllers could be programmable logic controllers or PLCs. or the remote terminal units or RTUs. And these devices are embedded devices to control the operation of standalone devices in power grids such as generators, transformers, circuit breakers, or switches. In another type of attack, the attacker might target the SCADA system or the computer network that is used for monitoring and controlling the power grid. And finally, we have the indirect attacks on the power grid. For example, the attacker might try to do the load altering attacks using the botnet. And we're going to explain it in the next few slides, what it means. Now, for each of the attacks, let's bring up some examples to see what we had, what historical cases we had so far. Regarding the first type of attack, attacking the controllers of standalone devices, we have the Aurora attack, which was introduced in 2007 by Idaho National Laboratory. And in this attack, there is a computer worm that is infecting the controller of the generator. It is opening the circuit breaker of the generator and then closing it at the right moment to cause a huge mechanical tension in the rotor of the generator. And this finally leads to the explosion of the generator and the destruction of this piece of equipment. So it was a serious threat, which was discovered and introduced in 2007. From the second type of attacks that the attackers target the SCADA system, we have many historical cases. Some of the notable ones are Dragonfly version 2 and Black Energy version 3. In Dragonfly version 2, the attackers targeted several utility companies in the United States, Turkey, and Switzerland and caused regional blackouts. So there were many people who lost power for many hours because of these attacks. And in Black Energy 3 is the most famous actually malware targeted the SCADA system. It was used to target and for targeting and taking down the Ukrainian power grid in December 2015 and December 2016. And these two attacks were the most notable attacks on the power grid so far. And it was after these attacks that the power grid security started to gain attention from the researchers and the practitioners. Regarding the indirect attacks on the power grid, it was before thought that we don't have any control to the end users and the power consumption of the end users. But after the introduction of the IoT botnets, we noticed that the attacker might try to compromise a bunch of high wattage IoT devices, such as electric ovens, HVAC systems, water heaters, and then turn them on or off maliciously at the same time to cause technical problems in the grid. So this attack is called a manipulation of demand IoT or MAD IoT, and it was first introduced in Usenix Security Symposium in 2018. So basically, in this case, the attacker targets the bulk power grid, and it tries to turn on the compromised devices at the same time from random nodes or location in the grid to cause technical problems such as frequency instability and voltage instability, and finally lead the grid towards instability and blackout. Actually, in this research, in the research that was presented in Usenix Security, the authors showed that how this attack can cause large scale problems and long-term outages in the power grid. But 1 year later, another group of researchers came in the same symposium, Usenix Symposium 2019, and presented not everything is dark and gloomy. Basically, they claimed that it's not as dark as it was presented before. Because some of the existing and embedded power system protection schemes, such as under frequency load shedding, under voltage load shedding, or other controllers, were ignored in the previous research. And if we model them properly and include them properly in the grid, they can withstand against the mad IoT attacks and prevent the system from large scale collapse or blackout. So if we launch the attack randomly from random nodes and location, it was shown that it's not as effective as it was shown in most of the cases. So we won't see that much of serious problems in the grid. Now let's take a look at some of the recent natural blackouts that happened in different countries around the world. Obviously, we have so many blackouts happening in recent years, but the point is that they happen although they're affecting a lot of people, but they happen quite rarely. Like in every year or every 2 year, every 3 year, we have a serious blackout, large scale blackout. The reason that these are rarely happening is that the natural events usually do not happen in the weak nodes from the stability perspective. For example, if we have 100 nodes or 100 locations in the entire grid, if the event happens in one vulnerable node, it might lead to instability, but from a probabilistic point of view, this usually doesn't happen. But if we think about it, if we know the weak nodes of a power grid, of a given power grid, can we somehow mimic these primary causes to cause blackout in the grid intentionally? Like, can an attacker create this intentionally and target the weak nodes? In this case, we can cause blackout in any given grid more frequently and more maliciously. So let's talk about the threat model of our research, which is smart IoT. So we're claiming that instead of launching the mad IoT attack from random nodes that was previously proposed in the 2 previous Usenet security papers, we can change the load in specific nodes or locations. And we show that if we do this, it turns out to be more catastrophic because we can choose these specific nodes from the stability perspective. We can choose the nodes that have weaker or lower stability margins from the frequency stability and voltage stabilities, and target the grid from those perspectives. But obviously, we need some more information. So instead of the previous works that they randomly just turned on the devices without looking at the grid data, here we need detailed information about the grid operation to find out about those specific weak nodes. And also our botnet should be distributed among all the nodes and the geographical area in the grid so that if we identified or when we identified the weak nodes in the grid, we can target those points. So these are the 2 main requirements of our attack to be successful. So smart IoT has 2 main stages. In the first stage, we need to obtain the topology of the grid, which can be represented roughly by a graph. In this topology, we have some vertices and edges. Each vertex actually represents a node. And in the bulk power grid, each node represents a big city or a big power plant or anything like that. So we can obviously estimate the graph of the grid by using reconnaissance tools. And this can be done offline because the graph of the grid needs to be obtained for only one time. It doesn't change because you cannot change the big transmission lines or power plants or anything like that. And this can be done with semi-automatic ways. For example, you can use the satellite pictures and use the computer vision approaches to obtain this graph. And there are some of existing open source tools to obtain this with very high accuracy. And the reason that this is feasible is because that the bulk power grid, in the bulk power grid, everything is outdoor. Like you cannot hide the power plant, you cannot hide a big transmission line. So the second thing in the first stage is that we need to obtain the power grid operation data and map this operation data to the obtained graph to see in which node of the system or in which node of the graph we have how much of power generation and consumption. So this can be easily done by crawling the ISO's websites or independent system operators website, or using a trading tool called Bloomberg Terminal. And for example, this graph here shows the snapshot of the New York ISO website. You can see from different locations, we know how much power is generated and how much power is consumed. So you can map this data to the obtained graph, and then you have the entire model or operation, that real-time operation data of the power grid. Once you obtain this data, you can then do your system analysis stage and move on to the second stage. And with some mathematical calculations, you can rank the system nodes from the stability perspective. So doing this ranking the system nodes is very hard to do in real time with exact way, because we have high dimensional nonlinear equations. But there are some approximation methods in the literature which helps you to do that very fast. For example, we use two well-known indices called voltage magnitude and model analysis to rank the system nodes and obtain the weakest nodes of the grid to launch the MAD IoT attack from those nodes. Now let's talk about the attack feasibility and see if this attack is feasible or it's not realistic. So the first point that we should talk about is the IoT botnet from the IoT botnet perspective. The historical botnets such as Mirai botnet and its variants had over 600,000 bots. And also IoT botnets are available for rent, and also their renting and building cost is very low and negligible. So these, according to these points, we know that IoT botnets can be easily generated or rented. Also, about the second assumption, do we have a geographical distributed IoT botnet? So if we look at this figure, which shows the geographical distribution of the Mirai botnet, we can see that it's been distributed among all the geographical areas around the world. So we can target almost any power grid that we want in the United States and in the European Union countries, and even in Asian countries. And how we can geolocate the bots as an attacker. So this can be trivially done by using the IP addresses, because there are some tools, available tools, that with very high accuracy, you can geolocate a given bot with the IP address. The second consideration is about the end user. Like if we use this kind of attack, what would be the effect of this on the billing statement of the houses, smart houses that have some compromised devices in them? We claim that this is quite negligible. According to our analysis, the additional billing statement would be something between 0.1% to 0.3% in the United States, which is quite unnoticeable. Like imagine that you're paying $100 to your electricity bill, and in case that you have some compromised devices and the attacker uses them to attack the power grid, in the next month it's going to be something like $100 and like 10 cents or something like that, which is quite unnoticeable. And in the worst case scenario, if you notice about the attack that in your smart home, if you notice that there are some devices in your home that are showing like weird behaviors, short-term weird behaviors, you might like detect them, but it's very hard because the attack duty cycle is very small, like 10 seconds. It usually takes like 10 seconds. If you have HVAC system and it turns on suddenly for 10 seconds and then it turns off, it's very unlikely that you consider this as a compromise of your own device. And in the worst case scenario, if you notice about them, individual bot detection and losing few bots would not dot the entire attack, because like this is a distributed large attack. Now let's take a look at the verification and some evaluation results to see how effective this is in practice. So obviously we used only simulation results because real world implementation has devastating effects and it's not possible. We used two standard test cases to compare with the previous works, IEEE 9-node system and IEEE 39-node system. And we did comprehensive system modeling to minimize the simulation error. And in this comprehensive system modeling, we used the detailed component and controllers and protective devices modeling, and also the system controllers and protective devices. For example, this table summarizes some of the things that were overlooked in the modeling of the previous works that we modeled in our work to have the most realistic results from the practical perspective. We did this comprehensive modeling and simulated the test grids using a commercial tool used by system operators called Dixilon Power Factory. It's a pretty powerful software that is used to realistically simulate the power grids. So we simulated the grid for both of the grids for 24 hours, and we periodically collected measurements every 5 minutes. But obviously we can extrapolate these 24 hours to any long-term simulation, because in every 24 hours we have a similar pattern for the system operation and system loads. And despite the previous works, because they only simulated the grid for 5 minutes, we simulated for 24 hours just to have a comprehensive analysis. For example, these two graphs are showing the load profile of the two test systems. This is the 39 node and this is the 9 node test systems. And these two figures are showing the system graphs for the test systems, 39 nodes and 9 node test systems. For example, here we have 10 generators, a bunch of transmission lines and loads in different nodes. And here we only have 3 generators and like some loads in the system. So this is a smaller test system, but since it's a standard test system, we used it in our simulations. Now let's consider that we, as an attacker, we have access to a botnet with 150,000 bots, which is quite realistic. What would be the attack success rate in this case? So if you look at this graph, we can see that using the index 1 and index 2, and we simulated the like two previous works, we can see that the attack success rate using our indices is quite high. Like in index 1, it's around like 63-4%, and in index 2, it's around 90% success rate compared to the like 0 and 1% success rate of the previous works. The reason that this is happening is that, as I mentioned, we're finding, instead of launching the attack from random nodes, we're finding the weak nodes of the system and we're targeting those points to take down the power grid. Now let's take a look at the result that is associated with the effect of the botnet size on the attack success rate. As we can see here, as the botnet size increases, the attack success rate increases, but after some point it saturates. For example, after 150,000 bots in the grid, it saturates because with this amount of botnet power, we can take down the power grid at any location that we want. But what is happening in the grid during a typical attack? So these figures are showing the frequency and voltage profiles of the grid, simulating three different methods. The first paper, the second paper in the literature, and our own smart IoT attack. As we can see, if we launch the attack from random nodes, the existing system protection schemes and controllers are able to recover the grid to the normal operating condition. Like attack is happening here, the controllers and protection schemes are getting involved in here, and they are recovering the grid to here. The same happens for the voltage magnitudes. In the second simulated case, a similar thing is happening, but in our attack, because we're targeting the weak points of the grid, the frequency is getting recovered to some extent, but the voltage collapse happens in the grid, and a large scale blackout happens eventually. But what is the effect of the botnet time delay on the attack performance? Like, we know that we cannot turn on all the compromised devices at the same time. There might be slight delay between them. So we considered mean time delay for the activation of the bots in different nodes, and we know we increase this number. And as we can see, like even with 2 seconds of delay, which is a very huge delay in the activation of the bots, we don't have that much of significant effect on the attack success rate, and we still have a pretty high success rate. But now we know that it's an effective attack and it's a serious threat. So one might ask, so what? Like, who cares? Is it a big deal? Our answer to this question is yes, it is a big deal. It is a big deal for power grid operators because this attack is obviously threatening the reliability of the grid, and the power grid operator's main goal is to keep the reliability of the grid as high as possible. It is a big deal for the utilities and end users because such attacks can cause like huge economic damage and inconvenience to the end users. Just recall the recent events happened in Texas following the weather events. The people lost power for like 24 hours, and if you recall the news, you know that what kind of like chaos it caused in Texas. And also, it's a big deal for the governments because it's a national security concern, and every power grid in every country is considered among the most critical infrastructure. And such attacks could be used as a part of trade or Cold War. So it is a big deal for governments as well. But what we can do to defend against such attacks? Like, is there anything we can do to defend, to mitigate, or at least reduce the damaging consequences? So the first thing that we can do about it is that the government agencies such as FERC or Federal Electric Regulatory Commission could be involved in this countermeasures or defenses, because the main thing that gives the ability to the attacker to launch this targeted attack is that we're somehow getting access to the real-time operation data of the power grid. And this is clearly a data privacy issue. So we need some new regulations and policies here to not to share the real-time data of the power grid with anyone. So we shouldn't share those information with like in these online websites. Or we can do some delayed data sharing or sharing the redacted data to reduce the possibility and increase the estimation error of the attacker getting access to that data. The second countermeasure can be taken by the IoT vendors. Obviously, they can form a big giant IoT database to register a small portion of their IoT devices there, and they can monitor them synchronously. So obviously, if there is any like synchronous activation or deactivation of these devices in larger scale, we can call it as an attack, and we can like locate those devices, try to make them secure or patch them to like reduce the possibility of this attack in the future. Also, the utility companies can collaborate with each other and implement a strategy called non-intrusive load monitoring. Uh, and it's basically estimating the what devices are being used in every home by only looking at the power usage of the smart meter that is measuring the power usage of the homeowner. So obviously, if there is any unwanted usage of a specific device, this non-intrusive load monitoring can issue a warning to the homeowner saying that, okay, you have like 3 or 4 devices in your home that are showing suspicious behavior. Obviously, this can be done by using the machine learning based anomaly detection approaches, uh, which have been which have been which have been discovered and like researched in recent years tremendously. Also, we have some protection relays in the grid that if we revise their like protection algorithms, like the UFLS and UVLS relays, they can withstand against these attacks significantly. For example, we revised the UFLS algorithm in the grid and implemented some of the successful scenarios. And this figure shows what happens after the revision that was done on the grid protection. We can see that even after launching the optimum attack from the weak points, if we have the optimum or the best protection scheme or the well-tuned protection schemes, our system or the protection schemes can like protect this grid and can recover it to the normal operating conditions. So this is another research path or that can defend against these kind of attacks. So as a summary, we presented the high wattage IoT botnet and we showed that how it can cause power grid blackout. And we showed some short-term and long-term countermeasures that could be implemented to lower the risk of the attack. And we showed that the attack vector should be studied in other domains. For example, the same attacker can try, having access to the IoT botnet, can try to target other domains such as the electricity markets. So this was the end of my presentation. Thank you for listening, and I'm here for any questions. Thank you.